So this is more or less today's solar cell and the solar module efficiencies. But all these thin film solar cell, as to durability, they cannot compete with crystalline silicon. If so, then why community is so anxious to study thin film solar cell? This is important point. The point is silicon-based solar cell technology, although it is occupying more than 92% of the market, photovoltaic market, it has a lot of drawbacks. And in later slides, I will show it and tell it in brief examples, concrete examples of it. So then here are the examples of using solar energy in Norway, although it is less sunny as India, but still it's very popular now. Solar installations are going on top of roofs of schools and on open areas as well, and on mountain areas where it is hard to bring these solar cells. I mean the electrical wires. So there is a very strong need, very strong market, but not only in Norway, but also, and there are a lot of Norwegian companies that have a solar cell activity. One of them is Renewable Energy Corporation that has, and also Scatec Solar and Elkem Solar. For example, Scatec Solar, they have business in India and in South Africa, in Latin America, and this company, Renewable Energy Corporation, it is situated in Singapore and has business in Asia area also. So they are focusing on solar cell development, solar module development, and the solar farm installations. So one of the markets is Norway itself. And in Norwegian universities and institutes, we are focusing on solar cell fabrication and characterization, on materials development for solar cells. However, so far, the main focus of the solar cell research is about silicon-based solar cells. Of course, we have some groups focusing on perovskite solar cells also, because this is the perovskite solar cell activity is interesting to Norwegian companies. So the research activity, it should be aligned to interest of the Norwegian companies. Also near to Norway, in the city called Arvada, I think there is a company that are producing solar modules. It's called SWE Module. And we are producing silicon, but in the form of the silicon particles. In the near future, our aim is to use these silicon particles in solar cells from particles. But so far, we are using these silicon particles in energy storage devices like lithium-ion batteries, and also in medicine for drug delivery and for drug delivery systems. And we are producing the particles by Siemens technology. And at present, we have several reactors, Siemens type reactors for producing the particles. So as to the first generation solar cells, I already mentioned what stands for the first generation cells. To today, there are many designs of the first generation silicon based solar cells, and each of them it's prepared according to its with different technologies. It consists of different layers, and the most well-known one is, of course, industrial solar cells, that consists of emitter and the base layer and anti-reflection coating, passivation layer, and the front silver contact and back contact from aluminum. But the complete design is totally complicated these days. And many other new designs came out, and the new type of the silicon-based cells are heat cells, and also PERC cells, and a lot of solar cell designs are available. But now we will see how complicated it is to make these silicon-based cells, and why we are so anxious about thin film solar cells. Why we are looking for a contender that would be desirable to replace silicon. So here on the right hand side, you see three pictures, three images. These images are images of silicon wafers. In case if, and these images are taken by an instrument called PL imaging, photoluminescence imaging. And if the image is of blue color, it means quality is good, charge carrier recombination is low. And if this type of, a lot of red spots, this means the wafer quality is not so good. There are a lot of defects, and that is causing charge carrier recombination. So, so before using the silicon in a solar cell, one should clean its surface quite well. The cleaning can be achieved by HF treatment. And the chemical treatment of silicon surface itself is a very artwork, and it is very dangerous. In the HF treatment, it's a type of treatment that industry doesn't like at all because it's not safe to do. But since silicon is very durable material, and it is occupying 92% of the market, they are saying, okay, no other way, unfortunately. So then one should treat the surface of silicon by HF, and after this chemical processing of the surface of silicon becomes very hydrophobic. So it will be totally dry when you pick up after all the treatments. However, within less than 1 minute time, it gets oxidized quickly, and then one should deposit some additional layers on top of it quickly. So very special care should be taken for that. And what type of layers are there that should be deposited on top of silicon? And what is requirements to them? One is, of course, silicon oxide. Silicon oxide, it is after treatments of the surface of silicon gets oxidized, and silicon oxide will be formed. However, the speed how this silicon oxide is formed is too slow, and within 24 hours, about 2 nanometer thick layer will be formed, which is, of course, too slow. And one can speed up by heating. If one heats it up to 800, 900 degrees C, then of course oxide formation will be fast. However, another here, then the light reflecting properties will be not so good. From the back side. Then what to do then? Let's then heat up to at about, for example, 1100 degrees C. Then everything is okay. However, at very high such temperature, property of silicon itself will be damaged. Then let's then avoid it. Then, okay, what material should we use then? And the point is, after the treatment, if silicon is not encapsulated, then it will again just absorb other atoms from the environment. Upon illumination of the solar cell with sunlight, electrons holes are created, and we should pick them up and transfer them to metallic contacts. So what they would do, they would, instead of coming to contacts, they would die at the interface states. To avoid them, we should passivate the surface states. The surface states are coming from silicon, dangling bonds, and other atoms. Suppose all other atoms we have clean it by chemical treatment, then afterwards we should cover with something else. So that's why we need this like passivation layers, and that passivation layer should possess very wide band gap, it shouldn't absorb sunlight. And in the list on the left hand side, you see the list of the materials that are wide band gap. So now we see it is good to use silicon oxide, but there are challenges. Another candidate is silicon nitride, which is hydrogenated. When it's hydrogenated, its band gap is above 3.3 electron volt, and it passivates silicon surface very well. However, the passivation is very good, provided if silicon surface possesses N-type electrical conductivity. It should be very highly doped highly doped silicon surface, and it should be N-type. N-type conductivity can be done by phosphorus, and doping with phosphorus is not an easy task. Also, I should here mention one more point about the silicon wafers in silicon wafers. Yes, there are two types of wafers. One type is possessing N-type electrical conductivity by phosphorus doping. The other one is boron doped silicon that possesses P-type conductivity. P-type conductivity is very good wafers. It's easier to produce than N-type. However, the point is this good P-type conductivity is achieved by doping with boron, and if so, oxygen likes to enter into that silicon, whereas phosphorus doped one is somehow and there is less oxygen. And when P-type boron doped silicon is, oxygen forms complex with boron, BO complex, and that complex is metastable, and that reduces charge carrier lifetime. Because of that, many companies, some about 3 or 5 years ago, they were producing P-type monosilicon, but then they stopped it. Then started to produce N-type, because there was a question how to suppress, how to avoid formation of boron-oxygen complex. If it's formed, how it should be decomposed. That was and that is big problem. And so this is really a big problem. And then it's not so easy to dope with phosphorus, and N-type conductivity wafers are very expensive. Because of that, community are coming back to boron doped silicon again. So then other candidate is amorphous silicon, and you know very well, I think, this is also easy to produce. It is very unstable because of the Stebler-Vronsky effect. Another candidate is silicon carbide, carbonitride, silicon oxynitride. With the silicon carbide, carbonitride, and silicon carbide, passivation quality is not good enough. With silicon oxynitride, it is good, it passivates very well. However, compared to silicon nitride, it degrades very fast itself. There is aluminum oxide. Distinct from silicon nitride, it passivates both N-type and P-type silicon, N-type silicon also. The only point is that passivation quality is very good if deposition is done by sputtering. But if it's done by PECVD, which is compatible with silicon solar cell fabrication process, then it's not good enough. So with each of the materials, there are some certain problems with passivating. So except open band gap, except good passivating property, except deposition method, there is one more challenge. That's refractive index of these materials should be coupled to that of silicon itself. I will come to this one a little bit later. In addition to it, multi-stack layers have been considered as well. All of them, it's to provide good silicon surface passivation and to get good pin junction. The problem related to silicon dioxide I already mentioned. And as to the silicon nitride, I did not mention one point. This is also very tricky work, depending on the thickness of the silicon nitride. One should be very careful about deposition temperature and annealing temperature and annealing time. In this picture, as you see, the duration of the annealing and the temperature of the duration, it should be really well correlated. For example, if annealing is done at about 500 degrees C, then the annealing time shouldn't exceed just several tenths of minutes. Otherwise, lifetime will go down. Effective surface lifetime will go down. So to avoid it, to have maximum lifetime, one should keep certain durability and of annealing and a certain temperature. If low temperature annealing, which would be okay. So then longer annealing time would be okay as well. Yes, and also I mentioned it about coupling of refractive index of the encapsulant and the silicon. What I mean, when silicon surface is treated by HF and other chemical treatments, it is so shiny, reflective of sunlight. It reflects about 30% of sunlight, whereas we want to convert it not to reflect sunlight, okay? And then if that's the case, then we should minimize light reflection. For that, we need refractive index of the encapsulant and the silicon to be coupled to each other. To minimize light reflection, refractive index of the encapsulant should be and the square root and refractive index of environment, for example, air and the semiconductor. Silicon refractive index is about 3.4. If refractive index is of air is 1, so then square root would be 1.85, whereas it's n.9, 1.9 for silicon nitride. So silicon nitride best suits for to be both not light, as anti-reflection coating as and also as a surface passivation layer. Silicon dioxide's refractive index is around 1.85, but it is a little bit different. And I think it's 1.9 or 1.6. Yeah, I don't remember exactly. It depends on, of course, on what type of glass is silicon dioxide is it. And it will provide certain reflectance. But the best one is to today silicon nitride and also aluminum oxide. There is one more challenge that I was not mentioning about silicon. So in case of the silicon wafers, thickness is about 250 micrometer. Why is it too thick? We don't feel it when we are considering just one wafer. If we are making it solar module, in one module, in average, there is 36, 72 solar cells. And if we are considering on large area like a farm, then this weight becomes sensitive, very sensitive. It's rigid also. And why then we are why we are considering the large area? The large thickness of silicon. So the point is here in band structure of silicon. It is indirect bandgap semiconductor between valence band maximum and this is a conduction band minimum. They are located at different high symmetry points in Brillouin zone. To make this is and this indirect band gap is about 1.1 electron volt. To absorb sunlight efficiently, we need to extend its thickness. So this is, for example, solar spectrum, and the green color part, it is the one to be absorbed by silicon. If we make it thinner, then the probability of photons corresponding to indirect band gap, it is too small. Then the direct band gap starts to work. But the direct band gap, it is about 2 electron volt. Then we will cut down a huge part of the sunlight. great part of the sunlight that we don't want. It means we should use thick silicon wafers. So then all these deficiencies has led to the idea about let's then search for an alternative material that would possess direct band gap, absorb efficiently sunlight, and that doesn't use HF treatment. And then, as you see, all these now steps about HF treatment and the challenges related to N-type, P-type wafers and the dopings. As to doping, there is one more challenge I will tell in subsequent slides. Um, so, so these challenges, in fact, are initiating the work, justifying, motivating the work for thin film solar cells. And the other challenges are in transparent and conducting films. And not all silicon solar cells are using TCO layers, just some of them. The very popular one is ITO, it's indium tin oxide. It is very good, expensive, but the scarcity of indium is a problem. Zinc oxide is okay, it is used in many types of solar cells. When it's in between two layers, it's okay, but when it's used as outermost layer, that's then sensitive, then it will become sensitive to humidity when it's 200 nanometer or less. When it's above 200 nanometer, then sensitivity to humidity is not problem, but then electrical conductivity and color will become problem. And here also crystal abundance of chemical elements and annual production and price per kilogram is very important factors. As if we compare with magnesium, zinc, and Indi, then we see in logarithmic scale.
Microphone off ಮಾಡ್ಬಿಟ್ಟು ವಾಲ್ಯೂಮ್ ಗೊತ್ತಿಲ್ಲ ವಾಲ್ಯೂಮ್
What?
ಟಚ್ ಮಾಡಿದೀಯ ನೀನು ಎಲ್ಲಿ
Hello? So this is question or? Yes. So.
Please continue, sir.
Yes, okay. Then also the other problem is about emitter making process. If we consider N-type silicon wafer, we need to make a P-type emitter. And emitter making process is also very complicated. One should put a boron-containing compound on top of silicon after it's cleaned well, and then heat up the system up to 900 degrees C within about 45 minutes. Then only it's possible to diffuse phosphorus inside the into silicon and to form emitter layer. This is time-consuming and energy-consuming process, whereas it could be avoided if, as emitter, we use polymers. A lot of polymers nowadays, they have the polymers mainly they possess P-type electrical conductivity, and the deposition of the polymers can be done by chemical method. And this has led to a new concept called hybrid silicon-organic solar cell. However, organic polymers, they are not stable with respect to influence of ultraviolet light. Then now a new design of solar cell has been developed. According to it, emitter is located on the backside of silicon. And then silicon would absorb all UV or visible light, and emitter is here. Emitter is needed just as a pin junction. So this is another very important work which is going on now. So then now we have justified sufficiently why we need second generation solar cells. Second generation solar cells, they are low cost but low efficiency. And I would say nowadays that the efficiency of the second generation cells also quite good. And this terminology about second generation, it came out a very long time back. In about 1996, I think, 97, and in that time range, first and second, third generations. So, and if we see the efficiency table, then we see efficiency of the CIGS, it's already above 20%. Cadmium telluride based solar cell efficiency is also above 20% already. Module efficiency has been increased quite a lot. And the CCTS solar cell efficiency is of course smaller, but there is certain progress on that. So let's come back now to just the exact representatives of thin film solar cells. So one of them is cadmium telluride cells. First Solar, the company First Solar is the leader on cadmium telluride cells. It can be just inkjet printed, and it can be it is flexible, but there are certain problems about this type of solar cell. And so I will tell here about these problems. So one of them is toxicity of cadmium and availability of tellurium and the metallic contacts. And to make a good metallic contact to cadmium telluride is a challenge because it doesn't allow to select large choice of materials. And upon using a metallic contact and a heavily doped region between cadmium telluride and the metal will be formed that will influence also on the cell efficiency. Copper contact has been used, but then copper diffuses very fast inside cadmium telluride even at room temperature, and the copper provides a good recombination and that reduces charge carrier lifetime. So nowadays, antimony, tellurium, molybdenum-based metallic contact is used. Then also toxicity of cadmium, is it an issue? This question was discussed some time ago, but now it is evident that although cadmium itself is toxic, but it's not toxic when it's inside cadmium telluride or cadmium sulfide, because it's impossible to release cadmium from these compounds. It can be maybe at about very high temperature, about thousands of degrees. So then we are confident that cadmium is not released, so it cannot be the source for pollution. And then the availability of tellurium, this is a big problem to that. But this is can somehow be avoided because there are not much consumers of tellurium, and so up to today, cadmium telluride solar cell is surviving well, and yeah. So of course, and it's byproduct of copper mining. And one needs to find the sources for tellurium. Otherwise, after some time, it might become problematic. As you see, efficiency is already went above 20%. And so, yeah, availability of tellurium would be maybe the only problem. And of course, problem of the metallic contact. The next candidate is CIGS, copper, indium, gallium, sulfide, or selenide. Yes, this is a direct bandgap semiconductor. It can absorb sunlight just about 2 micrometer thick. CIGS can absorb almost the same light as the 250 micrometer thick silicon. So it is really a lightweight solar cell. But and its absorption coefficient is very high compared to silicon. It's high, and now efficiency is quite high also. And the band gap can be tuned by controlling the relation gallium to indium and then band gap can be tuned from 1 eV up to 1.7 eV. And this is a design of the CIGS based solar cell. It is very similar to that of the cadmium telluride cells. Just here molybdenum contact, substrate, and on top of CIGS, cadmium sulfide-based window layer, and then encapsulated with TCO. So I should mention that in the all thin film solar cell technologies, transparent and conducting layer will be used. and mostly they use zinc oxide based aluminum doped zinc oxide TCOs. Although I said it is sensitive to humidity, it's not standalone. It is encapsulated with another layer, so it is safe. And the here challenge is about sodium. Sodium should be present in the material to possess certain electrical conductivity and to have to control grain size. The reason is not still known. Why? And the concentration of sodium, it is coming from glass containers. However, in case if glass is not used, then sodium should be incorporated. Otherwise, the solar cell doesn't have, cannot be as high efficiency. Yes, so presence of sodium here is very important. Then methods of depositions, it can be done both CIGS solar cells and the modules can be produced by sputtering also. And this is a scheme for producing the solar cells and for producing modules. Yes. Now let's come back to CZTS solar cells, copper zinc tin sulfide. So in about 2013, this was very popular type of solar cell. In cadmium telluride, CIGS, and the CZTS, electrical conductivity can be controlled by controlling cation vacancies. So this is advantage of these cells compared to silicon one. We don't need intentional doping to get to control p-type conductivity. So then up to 2018, efficiency of the pure CGTS cells, it was too low. It was about maybe 6-7%, but then breakthrough has been achieved up to 10% efficiency, which is very promising, and the paper is published in Nature Energy in 2018. So, and the idea was performing heat treatment to provide diffusion of cadmium to occupy zinc and copper sites. So, yes. But with CGTS, the problem is it is electrochemically very unstable, and even I would say main problem probably is related to presence of tin. Tin is a multivalent element. It can be in 2+, 3+, and 4+ charge states, and the transition between them can be tuned. And when, for example, the CGTS is illuminated with sunlight, electron can be transferred from valence band to conduction band minimum. Conduction band minimum consists of tin states. And when charge state of tin is changed from 4+ to 3+, then tin starts to rearrange the lattice around itself. And as a result, even if the CGTS is deposited by magnetron sputtering and in very stoichiometric way, after some time it will become unstable material. And then I think okay now. Yes. Hello. Can you hear me? Yes. Okay. So let me then continue. Yes. And this is a roadmap developed in China about cadmium telluride solar cell, the upper table, and in the lower table, CIGS solar cell. In each year, it's a roadmap about efficiency enhancement and the production line. So this is a promising type of solar cells. The next one is antimony selenide based solar cell. This is compared to CIGS and the CGTS. Compared to CGTS, it is efficiency is right now it is a problem, but we hope it will be solved quickly. And now, and in 2000, I think 18, efficiency was about 6%. Now it's already above 10%. And it can be deposited by very cheap technique like thermal evaporation, the whole process. And the design of the solar cell is very simple also. So, but there is one big challenge related with this type of solar cell. It is how to control electrical conductivity. The lower efficiency, around 10%, 6%, is obtained because electrical conductivity of antimony selenide is not controlled at all. But how to control it? This is open challenge right now. And right now, community is using insulating antimony selenide. In cadmium telluride, CIGS, CGTS, they are using simple technique to control cation vacancy. However, in those materials, cation possesses two minus two plus valence state, whereas antimony here possesses 3 plus valence state. Then how to do it? This one should play around here. Only according to some theoretical predictions, chlorine substituting anion and cation vacancy. This type of complex might provide p-type electrical conductivity, but this is under debate at present. But this is a promising type of solar cell. It is band gap of the antimony selenide is about 1 electron volt. It possesses very high absorption coefficient, and the minority charge carrier mobility is of course it's too small. It's about 10 centimeter square volt second. Charge carrier lifetime is too small, and one should be able to control grain size. And the theoretical predicted efficiency is around 32%, which is high. So let me now come to selenium-based solar cell. So selenium, and this is one of the very first type of solar cells that converts sunlight into electrical energy. Its design is also too simple, just a few layers. And then when silicon and other semiconductors came out to the scene, community forgot about the selenium. But now community came back to selenium also. And the study of this material, of this type of solar cell, would give some promising results, I would say. And first of all, selenium possesses spiral type lattice, which is really very exciting, and many new effects could be expected from this material. And then the material can be and these new materials properties could be implemented into selenium-based solar cells. And yes, efficiency right now for about the solar cell is too small. It's about it's still less than 6%, but it's question of time, I think. It might go above 6% also. So then, in summary, I would say that thin film solar cells, they are the contenders for silicon solar cells also. And one contradiction that I briefly mentioned it in my presentation. It is that according to definition, second generation solar cells are it's low efficiency, low cost. But nowadays, it is efficiency is high. It's above 20%. When it was second generation solar cells, thin film solar cells, in those days efficiency was around 16, but not more. But now it's above 20. So then it's entering as to efficiency to first generation solar cells, high efficiency. But of course, they cannot compete with silicon about durability. And the technology of producing became more expensive than it was before, but it's not as expensive as silicon. So thank you for your attention. And I would like to leave the rest a few minutes for questions. And in case if you have more questions, of course, you are welcome to send to my email or just contact me by WhatsApp. So yeah, now we are open for questions.
Hello.
Yes, so now we are open for questions. So yeah, feel free to ask questions.
Hello, sir.
Yes.
Sir, I have one doubt, sir. Actually, we are working in gallium nitride-based material for RF applications, and may I know what kind of software tool you are using for simulating your solar cells before fabrication, sir?
So sorry, it's a lot of this echo is coming out, and I couldn't hear the words. Maybe you can write in the chat system if it's okay.
Okay, sir. Okay, sir. I'll type in the chat box.
Yes, please. Okay, so I will show slide number 36. Yes. Yes, this one.
ವರ್ಡ್ ಗೊತ್ತಾಗಿಲ್ಲ ಫಾರ್ ಯುವರ್ ಸಬ್ಮಿಷನ್ ಒಂದು ಇದನ್ನು ತಕೊಂಡ್ಬಿಟ್ಟು ಉಳ್ಕೊಂಡ್ಬಿಡೋದು
Hello.
If you want, I can revise the presentation and send to you. That's no problem. Just I need to remove certain institution related info. Otherwise, I can send you. Yes.
Sir,
Slide number.
what?
Lot of noise.
Sir, what TCAD tool you are using for simulations?
Hello. Yes. Yeah, we are using for simulations of materials, properties, and defects. We are using VASP, real ab initio simulation software, and for modeling of device, we are using Silvaco. And experimental tools that we have are magnetron sputtering, PCVD, and these are the techniques that we are using. Mhm.
Okay, sir. Thank you, sir. Thank you for your informative session. Thank you very much.
So, and if not more questions, you can just send me. I think I feel here the problem about noise. It's hearing is very bad. So just send me maybe in written form questions. You know my email address. I will forward today afternoon copy of my presentation to organizers. So yeah. Yes, then thanks for your attention, and I'm very thankful to organizers for arranging this lecture. Yes, is tellurium used in what size? That as to tellurium size, I don't know.
Sir, actually, okay,
But
sir. Can I
yes, this is a very rare elements, of course.
please? So, okay, sir. Thank you so much, sir. We have to come final session. We have to vote up. Thanks,
Yeah.
sir. Actually, your presentation is so nice. Okay, sorry, due to some network issues, last minute we have to send the mail. We arrange for everything in last minute only because of network issues. And first of all, I got to thank you for management and the principal, sir. I give you a lot of opportunities to arrange this type of international webinar. So I very much thank you for management. And I particularly I thank so much my HOD sir. Is a friend like he motivate and organize like this type of seminar. So thanks so much, sir. Without your experience, we can't do this type of webinar. Thanks so much, sir. Sumakil sir, so you were more than 10 years. We have good friends, Sumakil sir, and we are doing the same solar energy in the field of nearly 10 years in CAT. I met many times in Coimbatore Institute of Technology. So thanks so much for your presentation, sir. When you have time, come to in India. Please come to our institution, sir. Then I want to thanks for our department colleagues. They have give lot of support in beginning of this international seminar. I particularly thanks my friends. Okay, they give the chance to arrange this type of seminar. Thanks so much, sir. Thanks everyone to participate. Participant, your support is very. Thank you very much. We have to conduct in future a lot of seminars due to your support. Thanks so much, sir. So actually, I sent the feedback form on your charts. You have to fill and get it your certificate. You will get on your mail. After you fill the link, you will get the certificates. Sir,
Okay. Yes. Thanks a lot
thanks.
for listening to me and for administration for giving the chance. So, yeah. Okay. Thanks. Bye bye.
Thanks. Bye, sir.
Thank you, sir. Thank you very much.
Thanks so much, sir. Thanks so much. Thank you, sir. Bye.
Thank you, Raja.
Thank you, sir. Bye, sir. Sir, எப்படி சார் சேவ் கெட் பண்ணுறது சார்?